Welcome to the third video of this section. Here, we're going to talk about matrix conversions. This is a very useful topic, as most of the time, you'll be doing matrix conversions in order to get an array into a desired shape. In this video, we'll learn how images are turned into matrices and represented inside the core machine learning application. We learn about how multiple images are stacked into a 3D matrix, how images are shuffled, and how different sets are segmented out. Here, matrices are just multi-dimensional arrays, and we're going to treat them as a matrix, because mostly deep learning concepts are related to matrix multiplication and addition, and you need to have an idea about the rules of matrix multiplication and addition. For example, in A cross B, the rule for matrix multiplication is that the number of columns of the first matrix A must be equal to the number of rows of the second matrix B. Then the output matrix dimension will have the same number of rows present in A and the number of columns present in matrix B. Also, in A plus B, both A and B should have the same number of rows and same number of columns. The same rules apply here as well. Let's dive deep into the method we covered earlier. Notice we read the pixel data as float point numbers. We then subtract the pixel depth, the number of pixel shades possible, and divide by 2. This centers the image around 0 and then distributes values between 0.5 and negative 0.5. If we had color images, we'd have 3 layers here, one each for red, green, and blue. For now, let's keep it simple. Our not-emness set consists of homogeneous 28 by 28 tiles. These images get represented in a matrix of floating point numbers, like this one. This matrix contains alphabets from letter A through letter J. This seems like a small image, but as letters are a less complex shape, so our deep learning classifier would be able to learn it pretty well, even with these low-resolution images. As more and more images are loaded, they are stacked on top of one another. While the original 2 dimensions are kept frozen, the stacking can be shuffled, and frequently it is. We also take the stack and segment it into different sets, keep track of starting and ending indices on the final axis. This is just for the storing of the images into memory after being read from the image files. Later on, as we're going to implement a simple logistic regression, we're going to reshape this image into a 2-dimensional array, where each row will contain all the pixels of an image, and will have rows equal to the number of images we're going to train with. Also, the column length will be equal to the number of image pixels that we have. That is, 28 by 28 is equal to 784. So, suppose we're going to train on 1,000 images, then the matrix dimension will be 1,000 into 784. It can be confusing, but we typically use the same methods to prepare both the training validation set as well as the test sets. When processing the test set, we don't segment out a subset for validation. The entire test set is used just for testing. We often pickle the end resulting set. This saves the files in ready-to-use manner and allows us to skip many steps. The pickle files can be loaded and used right away, skipping many of these steps. The training set is typically broken down into a large portion, which remains the training set, and a smaller portion used for validation. All 3 sets are kept using the same data structure, a stack of 2D matrices, one upon another. It's very important to not intermingle the test set with the other sets. The test sets provide us a realistic view of how good our classifier is, so it should not be used to actually train the classifier. To get a basic idea of the differences between each dataset, we have our training dataset to train our classifier. This is the only data that our classifier is going to see to actually adjust its parameters. The validation dataset is to analyze how well our classifier is training on our trained dataset. Validation accuracy tells us that our classifier can predict data that it has not seen before, and it also helps us adjust our hyperparameters, parameters that we adjust to train our classifier better. Although validation dataset is not fed into our classifier, we're adjusting our hyperparameters based on the valid accuracy, so our outputs can be biased and not generalized. That's why we need another dataset, which your classifier has never seen, not even through us, hyperparameters adjusting. This dataset is called the test dataset. So, in this video, we learned how to take raw images and turn them into matrices consumable by TensorFlow. We then learned how many such images are managed internally as a stacked 3D matrix. Finally, we learned about the different datasets typically used in the process and how they are often stored for quick access. Now that we've loaded images, automated the initial steps, and understood how the image is represented and managed internally, we'll start with the actual machine learning lifecycle. See you there.